Hello everyone and welcome back to this online NPTEL course on aqueous geochemistry. In our previous lecture we were discussing about redox reactions and I informed about the different types of oxidation states that each and every element can be in depending on the prevailing conditions of pH, the redox state, that is the dissolved oxygen state, the ORP value, the oxidative reductive potential, which can depend not only on the dissolved oxygen, but also on the presence of other oxidants and reductants, oxidants such as nitrates, hypochloritates. That oxidizes other metals, and similarly there will be other reducing agents as well. An extremely important aspect of solutes that dissolve in water is their state of existence in the water. So, therefore, understanding aqueous complexation, speciation is extremely important. That is, at what configuration they are there in the water, that is in the dissolved state. Okay. In the particulate phase, they will obviously be with the particulate bound in as different minerals. So, that becomes very strict because you have minerals, you will have the strict formulas. But when we are talking about dissolved states, there can be many transient states in which a particular element can always be moving. Okay. So, for certain elements the speciation is very easy. Okay. It can only exist in few states. For certain other elements the speciation can be very complex because it can form multiple types of complexes. So, it all depends on a lot of fundamental chemistry that depends on atoms, electron pairing, electrostatic forces, different types of bonding, the other constituents in the water, especially organics. Okay. So, all these will determine how the elements will behave or be in their aqueous state. To understand this, today we are going to dive in this lecture called aqueous complexation. Okay. So, moving ahead, so the first thing that we I would like you to have a very general understanding. Okay. So, most trace elements and their major ions, they are not transported or exist in their ionic forms. Okay. Mostly they will be in their complexed form. Okay. That means they are charged particles, right. So, they will form bonds, they will form a complex. Okay. Now, what is a complex? A complex is a dissolved species that exists because of an association of a cation and an anion, or maybe with a cation and a neutral molecule, or with an anion and a neutral molecule. Okay. So, complex can be many types. There can be n number of permutations and combinations, they can have different types of stabilities. So, most commonly we find that dissolved metals, they do not stay in the free ionic forms. Very few percentage of metals will be certain species which would not even if they are being in their free ionic forms, they will be surrounded by certain ligands and all that. So, even if they are there as free ions, okay, their complex formation can always continue. Okay. And I will tell more about this I will explain more about this in the few slides as we move. Complexes, what is a now complex, as I just now mentioned, right, that it is a combination. Now, instead of a molecule we can have something which is called a ligand. Okay. So, a ligand is also something which is like an anion or a neutral molecule, and it can be even an organic molecule, and in fact many times it is the complex organic molecules that have these names called ligand. Okay. So, ligand is basically an anion or a neutral molecule that can combine with a cation to form a complex. Okay. And such aqueous complexes control the solubility, mobility of particular not only particular metals, for them it is very important, but for most elements it is extremely important. Okay. Now, complexes therefore are important for 4 reasons. The first, as I just mentioned, that complexing increases the solubility of a mineral over its solubility if the complexing agent was absent. Say for instance, you are doing a completely controlled experiment in the lab. Okay. Because of the lack of other constituents in that kind of experiment, where you are using very pure substances, you are mixing them, then their solubility you are checking and it may take some time. But in a natural system where there are lot of other constituents mixed, so it is like a potpourri of different elements, right. So, there a lot of complexation can happen, and you can expect that, because they are always some kind of charged particles, and electrostatic forces are there, there will be these covalent forces will be there. So, because of these unneutralized forces, there will be complex formation. Okay. Second thing is adsorption. Okay. This phenomena of adsorption is part of a complex formation. Okay. Why do we have adsorption? Adsorption is formed because there is some kind of particle which is feels a kind of attraction towards a particular surface. Adsorption is always a surface specific phenomena. Okay. So, whenever you talk about adsorption, you need to have a surface, and on that surface a particle will come and adsorb. Okay. Same thing I will discuss about adsorption in more details in the future slides. So, for now adsorption of cations or anions may be greatly favored or inhibited when they occur as complexes rather than as free uncomplexed ions. Okay. Just due to their electrostatic bonding nature, free what is a free ion availability, okay, their complexity can be very favorable for adsorption. Also, the dissolution of some metals is higher if they are in their complex form. So, some elements occur in solution more favorably as complexes than as free ions. For example, the most heavy metals, toxic metals like copper, mercury, lead, even redox sensitive metals like iron and uranium, they are found chiefly in complexes rather than as free ions. Okay. The toxicity and bioavailability of metals in natural waters depends on the aqueous speciation or complexation of these metals, and the toxicities to aquatic life for copper, cadmium, zinc, nickel, mercury and lead are a function of the activities of the metal ions and their complexes and not of the total metal concentrations. What do I mean by this? I mean by this is that certain metals, these metals, okay, they are mostly found as complexes. You will never found them, you will rarely found them as free ions. It is not that you will not find them, you will find them maybe in very rarest of the rare cases they will be in their free ionic forms, and that is also mostly if you are doing only experiments. In experiments also, if you have a little bit of bicarbonate or some hydroxides and all that, it will always form some kind of complexes and they will be in their complexed form. Otherwise, they will not be soluble. Okay, otherwise they will not be soluble. Now, when we are doing water quality studies and we are trying to find out how a particular element concentration can affect the biota or any kind of particular aquatic species that you are considering, say suppose a fish species, okay, then what we need to calculate from the total concentration is their bioavailable concentration. That means that concentration that is available for uptake by the biota, that is called bioavailability. Okay, that means it is available for the biota to pick it up. Okay. So, say suppose I have 50 micrograms per liter of lead. Okay. Now, this is an extremely high concentration of lead, but out of that if I see that okay 49 microgram per liter of lead is complexed to certain in a form that it is not bioavailable, extremely difficult for any plant species or animal species to uptake that, then I will say okay only effective bioavailable percent is this 1 microgram per liter. So, when I am considering my risk when I am calculating my risk indices for that species, and I will calculate only this bioavailable fraction and not this entire concentration. Okay. So, every time we do water quality, we should realize this, that it is not the entire metal concentration available for the aquatic life. It is only the bioavailable fraction. That is why speciation studies are so important and fundamental to understand the impact of the particular metals that you have in mind or you are worried about. Okay. You should be able to do the speciation, and then only you can say that okay this much of the element is bioavailable and this is beyond the tolerant tolerance level of that particular species, and therefore, we should be taking necessary steps to prevent so and so poisoning or so and so can affect the life of that particular species. So, bioavailability studies depends on speciation, aqueous complexation, understanding of aqueous complexes and all that. Now, we will move into a little bit on the fundamental chemistry to understand why is it that is happening like this. Okay. It is all due to this unique dipolar structure of water. Okay. So, water has this unique dipolar structure. Okay. So, if this can be, if this you can see the structure, okay, you will see this is the oxygen atom and these two are the hydrogen atoms. And you know that oxygen has 2 pairs of electrons that is not shared. Okay. These 2 pairs of electrons, okay, one here and one here, creates a locally unsatisfied negative charged area. Okay. And this particular electron, which is with covalent sharing with the hydrogen, this again pulls the electron and there again this creates a local positive charge here. So, there is a distinction between the negative and the positive sides. So, here we have two negative charged areas and here we have two positive charged areas. Okay. And you see that this angle is at 104.5 degrees and therefore, there is enough space for coordination to form. Okay. So, this is the electron cloud. Okay. This is what is called the electron cloud, where the electron is freely moving, and it creates a distinct positive and a distinct negative charge spaces. Due to this polarity, okay, we have all other kinds of interactions. Okay. Let us see how we form complexes. Okay. So, because of this dipolar charge distribution, water molecules that in contact with cations, they will try to orient their negative charge towards a cation, right. So, here you have the two negative charges. Okay. So, it will start getting oriented towards the cation. And again this positive charged area where the hydrogens are, that will be charged, that will be again moved away from the cation, and that again here you can have another anion sitting here. So, by simple arrangement of the atoms, there can be this kind of charge distribution that can form with the electrostatic forces, they can form bonding. Okay. So, what we have is, so this is what we call hydrolysis, okay, of cations. Okay. So, because of this dipolar character, charge is unevenly distributed at the surface of each water molecule, and the protons of one molecule will attract the oxygen of the other adjacent water molecule. So, this attractive forces, which is called the weak hydrogen bonding, this controls the dielectric constant of water. What it controls? It controls this property called the dielectric constant value for water. What is a dielectric constant value? This particular parameter measures the solvent, for per se this is the water here. This controls this solvent's ability to dissolve ionic solids, and this value is higher for water than any other commonly found organic liquid. You can of course prepare whatever liquid of your choice in the lab, but for a commonly found liquid on earth's surface, water has the highest dielectric constant value. Okay. Now, because the bonding between molecules in minerals which are mostly of SiO or aluminum oxygen groups, they are mostly ionic. Okay. Because there you will see mostly the very so the alkali elements, alkali base elements, okay, they will be forming bonds. So, it will always be the ionic bonds, and water is an extremely good agent to dissolve these ionic solids. So, therefore, water is an extremely effective agent for chemical weathering, because it will dissolve these ionic bonds because of its high dielectric constant value, and it will just dissociate the components. Therefore, for silicate minerals, aluminosilicate minerals, water is extremely effective weathering agent. Okay. Now, let us see how does the complexes form, how does the complexes look like. Okay. So, here is an example where a water molecule is forming a complex with calcium. Okay. So, here we have the first our cation. So, this is our calcium. Okay. So, this is our calcium, and this comes directly in contact. Okay. As you can see, due to the arrangement, it is coming in contact with 6 other water molecules. Okay. And all of them, all the water molecules, they have directed their negative charged zones, that is the oxygen is directed towards the calcium ion. So, this is the calcium, and all the oxygen are directed towards that positive charge. Okay. And just depending on the arrangement, 6 molecules can fit in, that is directly in contact with the cation, that is here is calcium. Okay. So, this hydrated cation is what we call a calcium aqua complex. What do you mean by calcium aqua complex? That means my calcium has formed a complex with my water molecules. Okay. So, aqua complex, okay, it is in contact with this 6 water molecules, that is why we call it as the calcium aqua complex. Okay. Now, this region, okay, this particular region where there is a direct contact, okay, where there is a direct contact, this particular region is called the primary region. Okay. This is the primary region because the water molecules are directly in contact with the cation. There is also the impact of these bonds. Okay. So, here again there is a weak positive bond. So, the other water molecules, they will start putting their negative sides towards this. So, there will be a slight arrangement. So, till the level where we have some kind of arrangement of the water molecules is the secondary region. That means they are not in direct contact with the direct cation, but due to the orientation of the primary region, these water molecules also get slightly arranged, okay, but they are farther away from the cation. Okay. So, this is called the secondary region, okay. And there is another region where none of them, where this effect is not felt. So, this is okay beyond the second, this is beyond this region, that where it is scribbled. Okay. So, this region, this entire black area is the area where none of the water molecules are getting arranged. So, it is far away from the influence of this cation. So, therefore, there is no arrangement. Okay. So, they are unoriented. So, this is the zone of no orientation. So, you have the primary aqua complex and you have the secondary region where there is some orientation due to the polarity of the water molecules themselves, okay, where you will see that the water molecules are slightly arranged. Okay. So, this kind of aqueous complexes are continuously forming. Their stabilities can depend on a lot of factors. Okay. So, even though calcium is supposed to be in free ionic form, it can continuously form complexes just because of the polar nature, dipolar nature of the water molecule. Okay. So, this is called the inner sphere, the inner first circle is called the inner sphere and the outer circle is called the outer sphere. So, for the outer sphere complexes, they are called the ion pairs. Okay. So, it is association of a hydrated cation and an anion, okay, held by long range electrostatic forces. So, here you see there is no direct contact. So, instead of a water molecule, here there can be some anion as well. Okay. There can be some anions as well. So, this is a long range force that is acting. So, they are generally called ion pairs, that there is no strong bonding between them, they are just because of this long range electrostatic forces, they are somewhat oriented. Okay. So, this is called the outer sphere complexes. Their association is very transient and not strong, and often we find that the anion cannot displace the water molecules, that is an immediate contact with the water, immediate contact with the cation. Okay. Sometimes if it is a extremely strong anion, then maybe it can replace maybe one, but generally the inner complex is very strong. Okay. So, if any anion is there in the outer sphere, it will not be able to make its way into the inner sphere. Now, ion pairs are most often formed between major monovalent and divalent metal cations, and they are anionic, similarly they are major anions. So, it will be, for example, so the example is calcium sulphate. Okay. So, there will be calcium, there will be an inner sphere of So, calcium will be as calcium aqua complex, and there can be surrounding a lot of other water molecules, and there can be sulfate ion. Okay. So, these major anions and major cations, they always they tend to occur in such ion pairs. Okay. They will tend to form in such ion pairs. Now, all complexes in which the bond is chiefly electrostatic, they are considered as ion pairs regardless whether they have hydration around the cation or not. Okay. So, if the bonding is chiefly electrostatic, then it is considered as a ion pair. Okay. So, for example, they are all neutral molecules, okay. They are just paired, okay. They are just neutral molecules, they are paired, and their their strength is not very strong, they are not very strongly bound to each other, and this is the way it just exists in the water freely, okay. And this is the reason that all these elements remain very long time soluble, because they are always existing in these kinds of pairs. Okay. So, ion pairing and activity coefficient, these effects increase the concentration of species that is limited by the solubility of minerals. That is, even if the solubility of the mineral limits further dissolution, by forming ion pairing it can increase the solubility. Okay. In just due to ion pairing it can increase the solubility. Okay. As opposite to outer sphere complexes, inner sphere complexes are the ideal case, okay. And both of them will be there generally, okay. Inner complex will always have some outer sphere ring, okay. Most multivalent cations are aqua complexes, as I said, most multivalent cations, that is calcium 2 plus and Fe 3 plus and all this, they will be in their aqua complex state, and depending on the size of the atom it can be coordinated with 4 to 6 water molecules that will be bounded to them. So, aqua complexes, they themselves are the inner sphere complexes, and in case a ligand is coming. So, a ligand I said as can be a neutral molecule or it will be an ion. For them to form an inner sphere complex, it will displace one or more of the water molecules, okay. It has to displace one of the water molecules, and therefore, there will be some kind of covalent bonding character, because in covalent bonding the bonding is strong and it is more direct. So, it is now this ligand is going inside the inner sphere, okay. So, there will be more stronger covalent bonding kind of character. Cations form increasingly inner sphere complexes with a given ligand as their charge increases and the radius decreases, okay. So, if the charge is higher, so that is plus 3 plus 4, then their possibility of forming inner sphere complexes with ligands increases. Also, their atomic size has to be decreased, okay. Also, the atomic size has to decrease, so that the bonding electrostatic potential is high, okay. The higher this ionic potential, that is Z by R ratio of the cation, the more covalent its bonding it is in a complex, okay. So, the bonding that it forms with the ligand is more stronger, and the ligand has more stability in this bond, okay. So, examples of these kinds of inner sphere complexes are this AgS, mercuric iodide and uranium OH 3 plus complex, Okay. So, these elements they have multiple charges. Okay, they can exist in +4 state or they can exist as +6 state. Okay. And therefore, OH, which is the most common inorganic ligand, that will replace one of the water molecule. Okay, that will replace one of the water molecule and then it will come inside the inner sphere. Okay. So, trivalent and higher valent ions, they tend to form predominantly inner sphere complexes in general. Okay. They will form inner sphere complexes in general. So, this is a chart showing the apparent cationic radii, okay, that is the radius of the atom, and the charge of the cation or the cation in the complex. So, this is +1, +2, +3 charge and this is the radius. Okay. So, you have +1 charge and this is the way the increasing of the atomic size. So, lithium is here, your copper, sodium, silver, gold, potassium, all of these are here. So, they will generally form cations and aquacations. Okay, and this is the stability field for +2 charged. Okay, so this is there +2 charged. Okay, okay, so this I think is for oxyanions and this is the symbol for hydroxycations and hydroxyanions. Okay, so the filled circle is for cations and aquacations. Okay. The filled symbol is those which exist as cations or aquacations. Okay. So, this is the stability field. Then beyond this we have the stability of they will either exist as oxycations. Okay, they will either exist as oxycations or hydroxycations. So, either it will be in UO or UOH. So, for example, of uranium. Okay. So, in that state, so uranium exists in +6 states and uranium also exists in +5 states, and if it exists in +5 states then in a transient state. So, this is the stability. Again there is another stability here curve and these are oxyanions, they will be existing in their anionic state. So, this is the oxyanions. Okay. They will be more available in their oxyanionic form. Okay. So, this is the general stability that we find in aqueous natural aqueous systems. With this lecture I will stop here today and we are going to continue discussing more about aqueous complexation in our next lecture. Thank you.